Hi, in this video we'll discuss input normalization. Input normalization is an important step to speed up the training of deep learning models. This presentation focuses on the practical aspects of normalizing data for training models and the usage of models that have been pre-trained on the ImageNet dataset. So we'll examine why normalization matters through practical examples and understand how to properly use pre-trained models that were trained using the ImageNet dataset, which is a very important and foundational dataset in the deep learning community. So what is input scaling? It's a way in which we shift the position of the data, and it's a transformation that we do in order to make the training more numerically stable. We do this by subtracting the mean and then dividing by the standard deviation of the training dataset. This is called standard scaling, and it's the most common way that we apply scaling when we do deep learning. This sets the new mean of the dataset to 0 and the new variance of the data to 1. Notice that when we do this, the distribution keeps its shape, including any skew or multiple peaks that we might have before the transformation. This also allows us to preserve the relative distances between the data points. It's only that they are scaled now. This transformation does not distort the patterns that are underlying in the data. This is the most important aspect of it. Here we see that the mean and the standard deviation of the MNIST dataset have been computed, and we have used it to rescale the levels of intensity that we have in these images. We see that the histograms with the grayscale levels look the same before and after the transformation. We have only moved the data around. So why do we do this? What is the motivation for do this? It has been shown that it accelerates training of a neural network through a smoother gradient updates. And this also ensures compatibility when we use models that have already been trained and that use this normalization technique when they were originally trained. These are the two main motivations for us doing this type of transformation. This was popularized by a paper published in 1998 called Efficient Backprop. And in this paper you'll see a very detailed explanation about why centering the inputs around 0 speeds up the training. This is something that allows us to avoid some inefficient zigzag patterns when we update the weights, when we do a stochastic gradient descent, that would happen when all of the inputs are positive. This problem is something that would compound through layers, and this is something that would make training unstable. When we center the data around 0, like when we do with the standard scaler, we remove this directional bias, enabling us to have more direct paths to the optimal weights that we're looking for when we do a stochastic gradient descent. This foundational paper from Jan LeCun established normalization as a core practice in neural network training. If you're curious to go deeper in the analysis, please follow the link in the recommended reading materials. The standard scaler uses two very simple statistics from the training set. It's important to remember that these come only from the training set. We don't compute these statistics on the validation set or the test set. We compute the mean from the training dataset and the standard deviation from the training dataset. We see here that PyTorch allows us to implement the normalization through basically 3 lines. We compute the training set mean, we compute the training set standard deviation, and then we create a transform. These statistics are here being applied to grayscale images, where we have only one mean and one standard deviation. For RGB images, we're going to compute 3 pairs of statistics, 1 per color channel. So we're going to have in RGB, 1 mean for R, 1 mean for G, 1 mean for B, and the same for the standard deviations. So here's where we discuss the ImageNet dataset. This is a huge dataset that contains 14 million images organized in a hierarchy of objects. Each category in this hierarchy contains hundreds to thousands of labeled images. This dataset shaped modern computer vision and deep learning by providing enough data to train deep neural networks. And it's a dataset that is still quite significant. It's something that we are still using to benchmark new classification algorithms. And it remains free for research use. It was originally published about 15 years ago. And we'll see that the standardization statistics that we'll discuss for RGB images were computed on this particular dataset. And they are used in most pre-trained vision models because most pre-trained vision models have been trained on this particular dataset for image classification. So ImageNet was originally formed with the goal of populating something called the WordNet hierarchy with roughly 500 to 1,000 images per concept. Images for each concept were gathered by querying search engines and making humans annotate them through Mechanical Turk. So it has this type of hierarchy for the labels and is something that is quite detailed. The ImageNet challenge drove progress in computer vision and deep learning in the last decade, and here we see how significantly were the error rates dropped by the introduction of deep learning. When the AlexNet network was introduced in 2012, we noticed a big jump in the improvement of accuracy in the classification. When ResNet came in 2015, we basically solved the deep network training problem, and the models that you see on this particular slide became widely used, and we'll explore using them from their pre-trained state on the practical part of this video. The ImageNet normalization, as I said, separates RGB channels and processes them independently. Each channel is normalized using its specific statistics. And you see here what happens when we normalize this RGB image of an orange. And we have a mean for each channel and a standard deviation for each channel. After we do the normalization, most values fall between 1 and 2 standard deviations. This channel-wise normalization helps model learn color-specific features. So here we see a comparison about how ImageNet normalization affects the model predictions. Without doing scaling while using a pre-trained model, the model confidently identifies the orange. With proper scaling, the model confidently identifies the orange with 0.8 probability. Without scaling, the confidence drops to 0.5. And the incorrect classes gain some probability mass. The code shows the inference process. We just disable gradients, pass the image through the model, and apply softmax to get the probabilities, and then extract the top 3 predictions. This demonstrates why using the correct normalization statistics is important for pre-trained models. So PyTorch also provides a simple way for us to access the exact transforms used during model training. We can load a pre-trained model, access its weights object, and call transforms to get the pre-processing pipeline. The output shows all parameters. We see here that we do a center crop that is going to give us an output of 224 as the size of the image, but it first resized to 236. So this is an important detail. The resizing usually happens before cropping, and in this transformation for the conv next architecture, we see the output of what would happen step by step on one of the images that we worked before. So to summarize, we saw the importance of using this scaling technique to accelerate training. You're going to explore this in a more practical manner in the examples that you have in the Kaggle notebook. And we also saw the importance of applying the normalization technique when using pre-trained models created by optimizing performance on the ImageNet dataset. I hope that you find the exercises interesting, and I think that you will gain a much better understanding about this technique by using it in practice.